Hello, good afternoon, everyone. Our next talk is about sea level rise. I, for one, don't know everything about it, so we're going to hear more from it from Flo, and David, Bell, and James. We're going to talk more about it and test our knowledge. So let's see what we know.
Okay, so good afternoon, everyone. Today we wanted to deliver some message in a fairly different way compared to what we are used to do usually. So it will not be a normal presentation, but a quiz. So don't be shy. We will have some questions. If you want, raise your hand. But don't worry, if you mistake, we will not chase you after that. So because I didn't want it to play alone, so I invited three of my other colleagues that are here to the Cryosphere Pavilion with me. And so we will play all together and see if we know everything about sea level rise then. Okay. First question. Which of the following do not contribute to sea level rise? The thermal expansion of oceans, sea ice melting, glaciers and ice sheet melting, groundwater storage, local subsidence of coastal areas. Okay, so we think thermal expansion do not contribute to sea level rise. No one? Do you think that sea ice melting contributes to sea level rise or not? Okay. What about glaciers and ice sheet melting? Huh? Okay. Groundwater storage. Okay. Local subsidence of coastal areas. Okay, so the answer is sea ice melting. Sea ice melting do not contribute to sea level rise because sea ice is just the frozening of the surface layer of the oceans. So the water mass is already in the ocean, so it doesn't add up mass to the ocean, so it doesn't make sea level to rise. Okay, so sea ice melting do not contribute to sea level. Okay, cool. Thermal expansion of the ocean is something very important, as you know, because ocean is absorbing the heat. Okay, so as a consequence, it's a physical law of fluids. Actually, it just expands. Okay, horizontally and vertically. So the more we heat our system, and the more ocean absorbs the heat, the more it just inflates vertically. Okay. Of course, we are melting our glaciers and ice sheets, so we are contributing directly to sea level rise with that. Groundwater storage is an interesting component because of precipitation, evaporation cycle, the hydrological cycle, actually. And during one period, most of the water could be released into the ocean, while during glaciation, it tends to be retained inland. Okay, so those are the main components that contribute to sea level rise nowadays. Okay, other question now. How much did global mean sea level rise since 1993? 1 millimeter? 1 centimeter? 5 centimeters? 10 centimeters? What do you think? 10 centimeters? Millimeter? Okay. So the answer is 10 centimeters. And this is because we have been melting that much, but also expanding the ocean because of global warming, okay? As you can see on the map, sea level is not homogeneous, okay? Because it depends very much on the ocean currents, regions that are warming much than others, okay? Polar areas are still cold areas, okay? So you have land movements also, okay? So that's why sea level change, regionally speaking, is not homogeneous, but global mean, okay, is a calculation of the average of how much it raised, okay? So 10 centimeters, that's a lot, okay? What is the current rate of sea level rise? 1 millimeter per year. 2.1 millimeter per year? No. 3.6 millimeter per year. Yeah, a few answers there. 4.5 millimeters per year. So what do you think? What do you say? Yeah? 3.6. Okay. So answer is 4.5. but all the numbers are listed actually were past current rates of sea level change actually, okay? At the beginning, in the 90s and beginning of the 2000s, rates was about 2 millimeters per year, okay? Then it accelerated in the past decade to reach 3.6 millimeters per year. And now we are about 4.5 millimeters per year. So it shows you that sea level rise has been accelerating, okay? That's very important. Okay, another question. Amongst all listed items, which ones are possible consequences of sea level rise? Okay. So, permanently flooded land. Does it sound a consequence of sea level rise? Yeah? Storm surge, flooding. Yeah? Okay. Intra-urban floods. So what I mean by intra-urban floods is like when it's raining very much at one moment, okay? And then the water is have difficulties to drain into the ocean because the sea level is high. So yeah. Salty water intrusions. Yeah. Okay. Coastal erosion. Okay. Hold on. What did I do? Ah! Okay. So the answer is all of them actually. Yeah. So all of them are consequences of sea level rise, because when you rise sea level, of course, most of the water cannot reach the ocean after a rainfall, or even the rivers. I mean, at some point, most of the water will not be able to drain into the ocean, so they will flood lateral side of the rivers. Then coastal erosion, of course, because you will rise sea level, so the area where waves will be breaking on the coast will be damaging, of course, the integrity of the coast. Then saltwater intrusion, of course, because sea level rise, and then it intrudes inland in the soil, and all the rest we already said. Okay, perfect. No, okay. So now that we make a small quiz of introduction, I will let David to make a quiz about glaciers' contribution to sea level rise.
Thanks, Flo. All right, so we're going to dive into talking about glaciers now. So we do know that glaciers are responding to climate change. Here's a depiction of Rhone Glacier in Switzerland, 1850 and in 2000 there. So you see the surface is lowering as well as the glaciers retreating. Here's an example of a glacier in Alaska between 1940s and 2000s, right? So as these glaciers are retreating, all of that ice is melting and going into the ocean and rising. Here's where I did my PhD in interglacier in Nepal. You can see glacial lakes have also formed. So how much are the glaciers thinning each year? Okay, on average, all of our glaciers globally, is it 0.1 meter per year, about 0.5 meters per year, or about 1 meter per year? Meter? Meter? The average thinning is about 0.5 meter per year, okay? Now this is all of our glaciers globally, right? So that's a pretty high amount. But you can also see that it varies depending on the region where you're located, right? So in Alaska, for example, in southeastern Alaska, we have rates that are approaching a meter or exceeding 1 meter per year. In other regions, like in the Karakoram, where the Karakoram anomaly was, right, that had almost zero elevation change between 2000 and 2019, which has since started to change as well. So it depends where you are, but on average, it's about 0.5 meter. Cool. All right. Mountain glaciers. When I refer to mountain glaciers, I'm talking about the 200,000 glaciers that are not a part of our two ice sheets, right? Not the Greenland ice sheet, not the Antarctic ice sheet. They represent about 1% of the total volume of ice that we have on this Earth. How much, what percent of global mean sea level do you think comes from these mountain glaciers? I didn't give you multiple choice, so you're going to have to raise your voice. 1%? More? 25%? Roughly 20% of the contribution to global mean sea level comes from these mountain glaciers, despite those mountain glaciers just representing 1% of the total volume of our ice on the planet. Now we know that glacier mass loss is accelerating. This is one of the things that we can observe from remote sensing data primarily. There are many different types of remote sensing data and estimates that we have out there, but we can see that between 1960 and 2020, we see a very strong rate of acceleration. We also see, as Flo had pointed out earlier, that the rate of global mean sea level is also beginning to accelerate. Wow. What percent of that acceleration do you think is attributed to the glaciers? 16 to 18%. Fantastic job. Wow. You should take my class. So yes, glaciers explain about 6 to 18% of the global mean sea level acceleration. So they are quite substantial, but this is slightly lower than their contribution to the global mean sea level. So some of the other processes are accelerating a little bit more than the glaciers currently are. Now, as we move from the past into the future, right, we can start to use different general circulation models and different shared socioeconomic pathways to think about what's going to happen to the future of our glaciers. Here's an older example coming from the glacier model intercomparison that was based off of the RCPs. We've since updated these with the SSPs, but you can see that the glaciers are going to contribute between 80 and 160 millimeters of sea level equivalent moving forward. Now it's closer to about 90 and 150, depending on the SSPs. What percent of future global mean sea level rise do you think the glaciers are going to be responsible for? 1%? 10%? 20%? 15%? What is the answer? Sorry, good question. The same thing, 2015 to 2100. 10%, 15%. We see that it's roughly 20%. So the glaciers are still going to be a very large contributor to global mean sea level moving forward. There is some variability in here depending on what happens, for example, with the low likelihood, low confidence scenarios, which can start to change these percentages a bit. But for the most part, we're looking at around 20% continued into the future. And here's what I was showing is new projections. They estimate more mass loss. That means a little bit more of a contribution from the glaciers to sea level rise. We're estimating about 10 to 15% more mass loss than the glacier model and comparison results that were used to inform IPCC AR6. Now, will the glaciers continue to be a primary contributor beyond 2100? No. Yes. Beyond 2100, we do see that the glaciers are going to continue to contribute a lot to global mean sea level. However, what I really want to show is that you start to see large differences between 1.5 degrees temperature change increase relative to pre-industrial levels compared to a 2.8 degree scenario, right? So we can see these substantial differences in what's going to happen to the glaciers that are dependent on our actions today. And next up.
Okay, so now we had a quiz about the status of glaciers and contribution to sea level rise. So now we move to Greenland and Antarctica. So first question, if Greenland were to melt totally, okay, how much would sea level rise? And what about Antarctica, okay? So what about Greenland? 1 meter sea level rise on global average, 7 meter on global average, 56 meter on global average. What do you think? 7? 1 meter. Okay.
56.
56. Ah, wow. Okay.
There's two questions.
Okay. Greenland. Greenland. Okay. Antarctica. Okay, so for Greenland ice sheet, actually, it represents 7 meters of sea level rise if it were about to melt totally, okay? And for Antarctica, it's about 56 meters, split it in two parts, okay? What we call the western part, which holds 4 meters, and the eastern part, which holds 52 meters, okay? So Antarctica is much bigger than Greenland, but that's 7 meters, it's already a lot, even for Greenland. How does Greenland melt? And what about Antarctica? So Greenland, surface melt, basal melt beneath the land ice, so the ice that is on a continent. Basal melt beneath the floating ice, okay, on the ocean. What do you think about Greenland? 1 and 2, 1, 2, okay. And what about Antarctica? 3, 3. Okay, so for Greenland, you have all of 3, because Greenland also have some glaciers that ends in the ocean, okay? But it's not the major part of Greenland that melts because of the ocean, but Greenland is mainly melting at the surface, okay, because of atmospheric warming. And it melts a bit beneath because of the geothermal heat flux coming from the Earth, okay? And for Antarctica, it's effectively mainly oceanic melting below the floating parts of the terminating glaciers into the ocean. Antarctica very, very rarely melts at the surface for now, okay? So it's completely different than from Greenland. So as a consequence, Antarctica is very much vulnerable to future climate change in different aspects, because right now, if you remove the ice from the Antarctic continent, you can see that the brownish part of the topography below the ice is the one that is above sea level, and the light blue part is the part that is below sea level, and is lying on the ocean floor, so vulnerable to oceanic warming around Antarctica, okay? So in the future, Antarctica, unless Greenland, will be vulnerable more to atmospheric warming and oceanic warming. Okay, so that's the main difference with the Greenland ice sheet. With the Greenland ice sheet, the few oceanic glaciers will be retreating, and then most of the Greenland is terrestrial, so the problem will be different. Okay, does Antarctica contribute more than Greenland to sea level rise? What do you say? No? Yeah? No?
You mean right now?
Yes? Okay. So yes, no, it's contrasting. Okay. So no, the answer is no. Okay. Greenland contributes a little bit less than 1 millimeter, and Antarctica represents half of the contribution of Greenland. So nowadays, Antarctica contributes much less than Greenland. But in the future, we have potential for what we call massive ice sheet instability, so rapid discharge of a large volume of ice in the ocean. And this is because I was explaining before, we have this marine terminating glacier that floats on the ocean. And if we bring oceanic warming, if we increase oceanic warming, so the warm water will continue to flow below those floating platforms, and they will thin because they will melt from below, okay, and they will disintegrate, and it will trigger what we call step back in the grounding line. So the last point that the glacier touches the ground, actually, okay? It's a dynamical equilibrium of the ice sheet. It's the physics that's called marine ice sheet instability. Now, we have another one that, in addition to the oceanic warming, can have also some surface melt that infiltrate the crevasse and contribute to hydrofracturing of these floating platforms, okay? And so it creates another instabilities and a massive retreat back inland of the ice, and a massive discharge of ice into the ocean, and a rapid, large sea level rise, okay? What is the timing of those instabilities? A few centuries in total, from when they trigger to when it ends and find a new equilibrium. we have a very fast trigger that could happen now, okay? It's a tipping point or a threshold in oceanic temperature or atmospheric temperature, but when it passes, then those platforms disintegrate and the glacier has to reach it back, okay? And this can happens very, very fast in those decades, basically. But then the consequences are on the long term. I mean, the time that the glacier needs, the ice sheet needs to refine an equilibrium is a few centuries ahead in the future, okay? So if we trigger this collapse of floating platform, then the consequences will last for a long time, okay? So that's very important for that. This is a simulation illustrating this, okay? It's a part in the western side of Antarctica, showing that basically in 2 centuries ahead in the future, 2 to 3 centuries, the area can disintegrate, okay? That's the time scale of this disintegration, okay. Okay, now I pass over for paleo aspect of the ice sheet because it's important to have an idea of how they behaved in the past, to understand if it's normal how they behave now and how we project them to behave in the future.
Hi everyone. So the first question I have for you is, after that nice context that Flo gave us, how much we can expect from if Greenland and Antarctica were to melt. Do you think that that's ever happened? Has Greenland ever melted in the deep past of Earth's history?
Yes.
Seeing some nods. And Antarctica?
Yes.
Well, I'm showing here a slide from a 2015 paper. And now this is showing 4 time periods. On the left-hand side, we've got the present day. In the middle there, we've got a time period from 125,000 years ago, then 400,000 years ago, and then at the far side, 3 million years ago. And we're looking at the different estimates of sea level, global sea level, during these time periods. And we can see that we know that sea level has been higher in the past during these times. Most recently, approximately up to 10 meters higher than present day, with much of that contribution coming from Greenland and a certain amount from Antarctica. What I want to draw your attention to is the sort of estimates of temperature along the top there. So you can really see this quite clear relationship between the global temperature and the amount of sea level rise that we have. So how much have sea levels risen before? We sort of already answered that. Oh, that's the same slide. I'm going to investigate this time period in a little bit more detail. This is a period 125,000 years ago, just before the most recent ice age. This is a time period that we call the last interglacial. So interglacial being between ice ages when we have a slightly warmer climate and therefore higher sea level. We want to know what was going on during that time. How was sea level this much higher? And so this is actually an interesting table that sort of shows the studies that have gone on into this question through time and sort of honing in on an estimate for the different contributions from Greenland, from Antarctica, from mountains and thermal expansion to try and explain the observed sea level rise that we know must have happened in the past. And we can see that the most uncertainty that we have over sea level comes from Antarctica. We've really got this huge range of possible contributions to sea level from Antarctica. And the main target, the main culprit for this, we believe, is the West Antarctic ice sheet. Now, you might remember from one of Flo's slides, a lot of the West Antarctic ice sheet is sitting presently on land that is below sea level. And that's making it very vulnerable to ocean warming and these other instability processes that are causing significant melt in the West Antarctic. And we've seen lots of modeling studies go on into this question to try and understand the processes driving this melt. So on the left-hand side here, this is showing what might have happened during the last interglacial according to computer simulations models. And on the right-hand side there is a recent study that actually found observations for what would happen to the what might have happened to the West Antarctic. And you can see these estimates are incredibly similar, these projections of what might have happened. And this leads us to believe that the West Antarctic melt from the West Antarctic actually contributed around 6 or 7 meters to sea level during the last interglacial. And that was during times where the global temperature was probably about 1 degree warmer than today. And obviously, at the moment, we're headed for considerably warmer temperatures than that in the coming decades. And I just want to draw your attention to this one more time and maybe provide a bit of a context for what James will be telling you about very shortly. So this paper is actually maybe a little bit out of date now. It's from 2015, and it's showing CO2 levels, temperatures, and the corresponding sea level rise. But you can see that we're continuing to emit CO2. We're continuing to emit greenhouse gases. That CO2 level in the atmosphere is only increasing. The other interesting thing that the thing I find most interesting about Antarctica, I'm a paleoclimate scientist originally, so I'm used to investigating the climate of the past. This is the Antarctic ice sheet, so we can see that in places in the East Antarctic, it's several thousand meters thick. But what's really exciting about that is that it allows us to go back in time, drill these ice cores, and understand how the climate has changed in the past. We can also investigate the greenhouse gas levels in the past by analysing the contents of these little bubbles that get trapped inside the ice sheet. This is showing the last 800,000 years of CO2 in the atmosphere from Antarctic ice cores. Where it goes lighter blue, that's where we have these interglacials, these warmer periods. Where we have darker blue, we have lower concentrations, lower temperatures. That's our ice ages, when the ice sheets expand. On the right-hand side, we've zoomed in on the last 1,000 years, and this is showing really the context for what it is that we're going to be facing in the coming centuries. Because what we're doing to the planet at this point is pretty much unprecedented, at least in the last million or probably several million years. The science in this field is evolving very quickly. We're learning a lot more about the ice sheets. Historical data help us to more accurately predict future change by understanding more about these processes that are driving melt from the ice sheets and contributing to sea level rise. But it's quite clear that we have a pretty important choice to make in the coming decades about how this continues. And with that, I'll hand over to James, I believe. Thank you.
Thanks, Bella. So now we arrive to the part about tipping points and future projections and impacts. So I will be doing that with James. So back to some questions. Do you think that plus 1.5 degrees is enough to trigger irreversible ice melt? Yes or no?
Yes. Yes.
Yes, yes. Okay, so yeah, the answer is yes. And I explain a bit this graph. So on the horizontal scale, you have temperature warming in the future, okay? And the blue bar represents the plus 1.5 degrees warming, okay? And then you have all the components of the cryosphere here, okay? The ice sheets, Greenland ice sheet, West Antarctic ice sheets, marine-based East Antarctic ice sheet, terrestrial part of East Antarctic ice sheet, and the glaciers, okay? The bars, they represent the uncertainty that we have in the tipping point of the component of the cryosphere, okay? So it means that for some of the components, you can see the blue bar go across this temperature range of uncertainty, which means that possibly some parts of Antarctica and many of the glaciers already passed their tipping point. So it means that they already have, they are already showing some irreversible melting, okay? And it will continue in the future. Of course, the more we warm and the more we will pass tipping point for the different elements of the cryosphere. But 1.5 degrees is already enough to trigger on the long term massive retreat of Antarctic ice sheets, Greenland, and glaciers in some part of the world. So it means that even if we are very, very, very good in maintaining plus 1.5 degrees, we will anyway lose part of our cryosphere, okay? So this is something very important. If we stop emitting now, will sea level continue to rise?
Yes.
Yeah? Okay. And so this is because the ice and the ocean actually they are containing some kind of climate memory. They keep some climate memory. They are buffer components of the climate. Okay, so it means that under climatic conditions, both the ice and the ocean absorbs the heat a lot. Actually, currently, the ocean absorbs more than 90% of our excess of heat that we produce because of carbon emission in the atmosphere. Okay, so both ice sheet and the ice and the ocean absorb the heat. Okay, and sea level rise because, of course, thermal expansion of the ocean, because of melting of the ice and the glaciers. But because of this buffer effect, if we stop emitting now, if we go back to cooler temperature, or if we maintain temperature, several decades to centuries later, we will still have ice sheet and glacier to retreat because they will release the heat contained in the ice very, very, very slowly, okay? Because they have a very slow heat capacity and in thermal inertia. And that's the same for ocean. Ocean, if we stop emitting, it will stop absorbing the heat, but it already has a lot of heat inside. So it will still continue to bring the warmth to the Antarctic margins, to the glaciers, marine glaciers, okay, to the Arctic for sea ice melting. Anyway, so the consequences of the climate of our warming today are already committed for several centuries in the future, okay? So if we don't want the situation to worsen in the future, that's why we insist to keep under this threshold of 1.5 degrees, okay? Because most of the consequences, we will face them for centuries and our generations in the future. Yeah, sorry. So now I will let James to challenge you about the impacts of sea level rise.
Great. So first blow, who's having a good time at this side of it? Yay! Great. Who's done something new? Yay! Okay, great. So we know that sea level is now rising twice as fast as it was 30 years ago. That's a really scary thing. And the reason it's really scary is because it's already amplifying the damage caused by these extreme events. So we've seen terrible flooding in the US and the hurricane season in recent months, and sea level rise that we've already experienced because of the pollution of emitting fossil fuels into the atmosphere is making that worse. But how much worse? So how much extra damage did our existing anthropogenic sea level rise, which is about 23 centimeters, add on to the damage bill for Hurricane Sandy? Hands up for A, $8 million extra. Hands up for B, $80 million extra. Hands up for C, $800 million extra. Right. And there should be another one on this slide, but it seems to have disappeared. So it's actually $8 billion. $8 billion of damage caused by that extra 23 centimeters. And indeed, it was that 23 centimeters that made the difference between Lower Manhattan being flooded and not. Now, this is already having effects today. So these pictures are from a slide of a delegate from Tuvalu that I spoke to last week. Pictures from her home. And she's already saying that already now we cannot grow the food we used to grow because the ground is now more salty because the sea level is rising. We also cannot drink the water out of the wells that we used to drink because the well water is becoming more salty. And this means they're having to pay for water through desalinization and also import food from outside. So it's already costing them lots and lots of money, and it's making life really difficult for people today. Now, in terms of impact, we're split into short term, medium term, long term. First is coastal flooding. So this is the island of Kiribati in the Central Pacific Ocean. And these stats are from the UN Secretary General's technical brief on surging seas released in August this year. So in Kiribati, we've seen average flooding days per year, about less than 5 days a year, both in the 1980s, but also through to 2010s. That did not change. So how often will coastal flooding occur on average, the number of days per year by 2050 in Kiribati? Hand up for A, 10 days per year. B, 25 days per year. And I think C is about 65 days per year. So hand up for A, B, C. Okay. The answer is 65 days per year. That's about once per week, coastal flooding. Now, okay, what happens in the worst case scenario? So, sea level rise continues to accelerate. Hands up for A, 105 days per year of coastal flooding. Hands up for B, 165 days per year. And C, over 200 days a year. Answer is 165 days per year. Right, remember that one, right? Okay, that's about every 2 days. So these islands are going to experience massive coastal flooding frequency. It's really going to make their lives incredibly difficult. This is why SIDS are so concerned about ice loss in the polar regions and the corresponding sea level rise. They're affected more than anywhere else in the world. Now, saying that, it's not just SIDS. So because of the increase in sea level rise, unavoidable sea level rise now will affect about 1 billion people by the end of this century. And this map shows that the incidents per year, number of days per year, major floods just from the tides when sea level is 1 meter higher. So this means that floods which endanger lives, destroy infrastructure, cause huge amounts of damage will occur across the world globally, tens to even hundreds of days per year globally. And a bit of a spoiler here, that recent research is showing that most cities are adapting to this based on what we've previously experienced, not what we're having down the line. So really, we need to scale up the pace and the scope of adaptation to counter reflect exactly these big changes we're seeing beginning to start stirring in the ice sheets. So for Europe, this is quite a big thing. So this is the year when coastal flooding will become 10 times more frequent across the European coastline. What you can see is that it affects everywhere, essentially, and many of these changes happen in the next 3 or 4 decades. Now, this is under low emissions, but under high emissions, we see that not only does the number of locations that get flooded 10 times more frequently increase, but also these timelines are brought so much further forward to the next 10, 20 years. So this is why we can make a real big difference now by deciding a low versus high emission trajectory. Now, as well as this, many countries at this top are investing massively in nature-based solutions, like this is a salt marsh, also coastal mangroves. And these are fantastic nature-based solutions to sea level rise. They reduce erosion, they're a good source of carbon, and also they're great for biodiversity, so you can hit many of these things at the same time. However, because they are natural ecosystems, they have to grow upwards at the same rate the water is rising to survive. Now, recent research has shown that this is quite a big problem, because above about 7 millimeters per year, these natural ecosystems really struggle to keep up and will begin to retreat and die off. But luckily, at 1.5 degrees, most of the world doesn't hit that 7 millimeters a year or higher threshold. Under our current policies, the map turns red, and all of the areas in red here will begin to experience further erosion, retreat of these ecosystems, which means that all the money you're investing in these solutions may well be stranded. So how much will sea level rise in the future? It's a bit slightly messed up here, but what you see is that the first message is that we've locked them in already. We're talking IPCC between about 0.5 meter to 1 meter by the end of the century. How much difference can we make by doing low versus high emissions? So currently, under low emissions, we're talking somewhere between 0.5 meter and about 3 meters by 2300. If we continue on a high emissions pathway, we're talking minimum 2 meters roughly, but it could be up to 7 or potentially even more if these ice sheet instabilities kick off more rapidly. So this is a really big difference we're deciding today. What does this mean in terms of long-term existence of nations? So this is at 1 meter sea level rise for the capital of the Bahamas. You see that it begins to get kicked in. This amount is probably inevitable now in the long term, but if we act now, we can slow this down to hundreds or thousands of years. But if these ice sheet instabilities kick off, we could see this in the next 50 years or so. By 3 meters, the island goes underwater. It's not just SIDS, we also got Europe massively exposed. This is just 1 meter. This is Hamburg in Germany at 1 meter. And then at 3, it's massively hit. So think of the economic damage committed by our choices today in terms of our policies. This is Copenhagen and Malmo, 1 meter. 3 meters, the airport goes underwater. So imagine how much it would cost to resite Copenhagen Airport. Valencia at 1 meter in Spain, 3 meters. I'm sure the images from the recent flooding there from rainfall are still fresh in our minds, but what will we do when the flooding doesn't just come from the sky, but also from the sea? And we can't defend against this. This is the choice we're committing to by our current policies today. But it's not just the EU, it's also the biggest emitters. So this is Shanghai and China at 1 meter and 3 meters. In a similar way, Miami, famously so at 1 meter and at 3 meters. Finally, the LDCs, Karachi in Pakistan at 1 meter and at 3 meters. Dhaka in Bangladesh, 1 meter. By 3 meters, it becomes an island. So we're talking about having to potentially move cities if we continue to push our ice sheets more and more and more in the future. So I'm going to hang up the phone now to finish this.
Well, okay, so what I wanted to show to conclude this quick session anyway is what we know from the past archives of climate in terms of reconstruction of sea level rise and compared to our projections, because all those numbers we could think they are the produce of numerical modeling. They could be science fiction because we could run tens of scenarios, hundreds of scenarios, and we will get numbers between almost 0 and something between 15 meters, okay? But is this range completely science fiction? This is really important, right? Because what we want to understand is that, yeah, are they just probabilistic statistics on sea level rise, or can we trust anyway the range? So if we go back in the past, paleoclimate is very informative for that. So if we go back in the past, for example, you don't have to retain the name of the period, but 23 million years ago, it was quite warm, and CO2 concentration was above 500 ppm. Global mean temperature was about 5 to 9 degrees warmer than today, okay? Sea level rise was about 20 to 30 meters, even more, so it means that most of Antarctica was melted at that time. If we choose another period, 3 million years ago, okay, where CO2 concentration was just slightly higher than 400 ppm in terms of in the atmosphere, and global warming was about plus 2 degrees to 4 degrees. So it's something comparable to what we're projecting for the end of this century. Basically, we see that sea level range reconstructions span 5 to 15 meters, 20 meters. Okay, so because part of Antarctica and Greenland both melted. Another period closer to our present, 1.2 million years ago, temperature 0.5 to plus 1.5 degrees, so Paris Agreement, basically. CO2 concentration between 300 to 400 ppm in the atmosphere. Sea level range about 15 meters, okay? Higher than today, sorry. The most recent interglacial, big interglacial, 130,000 years ago, CO2 concentration below 300 ppm, global warming plus 5 to plus 1.5 degrees, okay? Sea level rise around 5 to 6, 7 meters, okay? What about our project? Okay, so plus 3 degrees, okay, our current NDC is actually, okay, plus 3 degrees. This is this period, about 15 meters sea level rise in average, okay? Plus 1.5 degrees or something close, okay? It's those two periods anyway, ranging about 5 to 10 meters, 15 meters, okay, of sea level rise. These are our projections. By 3 centuries in the future, okay, 3 centuries in the future, so 2300, we have something ranging a little bit below 5 meters for the Paris Agreement, and something about 15 meters for the worst case scenarios. So, compared to the period in the past, those numbers are not science fiction. Okay? So, can we trust the range of projections? Yes, we can, definitely. Do we know what will be the scenarios? No, because it depends on us. That's the thing. But the range is highly trustable and very likely in probability as well, compared to what happened to the Earth in the Earth's past climate history. So, in conclusion, ice losses have accelerated and they will continue to accelerate in the future because they are still absorbing a lot of heat. So once the melting triggers, then it's an exponential process. So it will keep accelerating in the future. Further loss of ice sheets, of ice and glaciers are locked in, of course, because of this buffer effect I mentioned. Okay, so even if we stop emitting, we commit to at least half-meter sea level rise in the future. And so adaptation is not an option. We will have to adapt even for a few centuries in the future, not only now, but even the future generations. Short-term implications of the sea level rise, we are already seeing them because each time we have an extreme event in coastal areas, it just couples. It's somewhat with sea level high tide problems or already global mean sea level rise that stops the water from draining into the ocean, increase the areas that are damaged by storm surges. So we are already seeing that. I mean, this is visible in many places of the world. So this is something that we have projected to happen already a few decades ago. Okay, the frequency of this intense event will, of course, increase in intensity, but the frequency, also will increase in the future. So the more sea level will rise, and the more damaging will be these events. Okay. The long-term implication, of course, as James showed, have long-term implication in terms of urban management of the territory, okay? Because it means that most of the territory that are very low lying in elevation, they will be flooded permanently. Some of them will be flooded every high tide. Some of them will be flooded in permanent way. So we have to deal with that. Because our city will have to move to migrate somewhere. We change the use of the territory of those cities. So we can still decide now the path that we want to do. It's still not too late to cope with the Paris Agreement, but every year we say that. So at some point it will be too late anyway. So that's why we keep pushing for this ratio to be respected, because in any case it has some big consequences in terms of adaptation of coastal areas. So if we want further, it will have even bigger consequences for us, and the costs of damages will be unbearable for populations for sure. Thank you very much for attending the quiz. Thank you to James, David, and Bella for challenging you. And have a nice rest of the talk and afternoon. Right. If you want to keep updated on the state of the cryosphere, the IC is publishing every year the state of the cryosphere report that we keep updating as scientists contributing to that. So download it on the website and keep on, stay tuned on the IC activities. Thanks.
Very good.
That was
fun.
Yeah, it was fun.
I like the interactiveness. This was a high tide flooding thing.